Hello everyone, this is Adnan and welcome to Chemistry with Adnan. On this YouTube channel, I'm covering the entire syllabus of IGCSE Cambridge Chemistry. The course code is 0620. And if you need one-on-one lessons, you can fill out the Google form that is given in the description and I will contact you. And you can also join my community on school.com. The name of the community is High School Chemistry, where I offer, a free lesson once a month. You can participate in discussions, you can post questions, you can interact with students from all around the world. It's an interesting place to be if you are learning chemistry. And there is a premium package where I offer, 4 lessons in a month, once per week, where you can, ask me questions directly. And, it's a small group and yeah. So now let's take a look at 6.2 rate of reaction. So in this lesson we will be covering the core topics, and then in the second part of this lesson or lecture we will cover the topics from extended or supplement syllabus. So if you are registering for or registered for October November intake, so the seats are very limited if you need one-on-one lessons. And if you are preparing for May June, so you guys yeah, so you can also book lessons with me. All right, so let's take a look at the first one now. It says that describe the effect on the rate of reaction of a changing the concentration of solutions. Okay, so what is meant by concentration? Concentration is a moles divided by a volume in dm cube, right? So the higher the concentration, and the more will be the particles. For example, if we have a beaker, and in this beaker we dissolve, let's say, 2 moles of sodium chloride, and it contains 250 milliliters of water, right? So we convert, or let's say, if it's like 250 centimeters cubed, it's the same thing. 1 ml equals to 1 centimeters cubed, right? So in order to convert from milliliter to dm cube, we divide it over 1,000, right? So 250 divided by 1,000, we get 0.25. So we have 2 moles. So let's use this equation, 2 divided by and 0.225, right? So 2 divided by 0.25, we get 8. So the concentration is 8 moles per dm cubed, right? So that is the concentration of this solution, right? So the point is, the higher the concentration, the higher will be the number of particles. And if there are more particles, there will be more collisions, and which will increase the rate of reaction, right? So changing the pressure now, uh, changing the pressure of gases. Okay, so again, increasing pressure increases the rate of reaction, because increasing pressure decreases volume, right? We already understand that volume and pressure, they are inversely proportional. So let's say I press this movable piston downwards on these gas molecules, it means that I am decreasing volume, right? And I'm compressing these. So as these molecules, they come closer, so they collide with each other more frequently as compared to when they have less pressure and more volume, right? So here we have now lower volume and high pressure. So again, when they will be colliding with each other more, so and the rate of the reaction will increase. So for concentration, increasing concentration increases rate, and decreasing concentration will slow down a chemical reaction. This is A. And B, this is the pressure change, right? Yeah, so increasing pressure will increase the rate of a reaction, and decreasing pressure will decrease the rate of a reaction. And now you understand the reason that why this happens, right? So because of less volume and more collisions. Okay, so I hope this is clear. Now we move on to the third part, which says that changing the surface area of solids. So what is meant by changing the surface area, or what is meant by surface area? Let's say we have a piece of paper. Okay, this is C, surface area, and let's say it's a piece. This is a piece of paper, and it has a surface area. So surface area is basically the area of a substance that is in direct contact with its surroundings, right? So for example, if this piece of paper is placed vertically, like horizontally on a table, right? It means that only the top surface the atmosphere can come in contact with, right? So we cannot touch the the side of the paper that is in contact with the table, right? This wooden table, for example, we cannot touch this side, right? Or the air molecules, it cannot touch the side, the back side of this paper, right? So if I shred this paper, if I put it in a shredder, and if I uh, okay, in this position, it will have a greater surface area as compared to the horizontal position, because now on both sides, the air particles or oxygen can interact with this piece of paper. But what about the atoms that are like within the layers, right? Like, or definitely there will be a top layer of atoms, and then there will be a layer of atoms lower than the top layer, and then so on. So the more you make it smaller, the more you crush it, the more you are increasing its surface area, right? I hope this is clear. And like you are making more surface of this thing available in order to have collisions. So surface area, increasing the surface area increases the chances of collisions with that substance. So that's gonna increase the rate of a reaction, right? So again, it's surface area. It's if you increase the surface area, the rate of the reaction increases, and that's how you increase the rate of the surface area of a substance, right? By cutting it into pieces, by crushing it and stuff. And decreasing surface area decreases the rate of a reaction. So imagine a piece of charcoal, a big lump of charcoal. So it takes time to burn, but if you crush it, and if you make it in a if you change it in a powdered form, so it's gonna burn very quickly, and all of it will burn at the same time, and it will be turned into ashes within seconds, right? And this thing, it takes time, because in the first step, the outer layer of the atoms will react, and then the more it burns, and the more atoms will get exposed, which are hidden inside, that are locked in this structure. And similarly, it will take more time. So I hope this is clear. Now we have the next one, which is changing the temperature, right? So again, temperature is also in increasing the temperature. This is D, temperature. Increasing temperature increases the rate of reaction, because the kinetic energy of the molecules, it increases, and the particles, they collide with each other. The particles, they collide with each other more frequently. Okay, so um, yeah. Now, we have adding or removing a catalyst, including enzymes. So catalyst and enzymes, they are basically the same thing. Enzymes are biocatalysts, and they are catalysts that are found in living organisms, right? So bio catalysts, and they speed up chemical reactions occurring in living organisms, plants and animals and bacteria and stuff, and even viruses. So, and adding or removing a catalyst. So definitely adding a catalyst will speed up a chemical reaction, and removing a catalyst will decrease the rate of a reaction. So temperature, and finally we have use of catalyst. So again, a catalyst will increase the if you add catalyst, the rate of a reaction will increase, and if you remove the catalyst, then definitely the rate of that reaction will decrease, right? And how does a catalyst work? It works by lowering the activation energy of a reaction. So each reaction, every reaction requires a minimum amount of energy for a reaction to occur, and that is called the activation energy. I think we have talked about this in our previous lesson. So if you haven't watched that lesson, you go watch that and then come back, and you will have a much better understanding of exothermic and endothermic reactions, and the activation energy. All right, so I hope this first topic is clear. 6.2, rate of reactions. And now we move on to the second subtopic, which is state that a catalyst increases the rate of a reaction and is unchanged at the end of a reaction. So what is a catalyst? So we define catalyst that it increases the rate of a reaction, right? So this is how you define a catalyst. And how does it lowers or increases the rate of a reaction? By lowering the activation energy. And one thing, this remarkable property of a catalyst is that it remains unchanged. For example, if a reaction is taking place and the reaction is A plus B, and it is producing C and D, right? And the catalyst that we are using is, let's say, E. So at the start of the reaction, we let's say we are adding this catalyst E to these reactants. So when we achieve the products C and D, when the reaction goes to completion, this E, the catalyst, it can be retrieved in its unchanged form, right? That is a remarkable property of catalysts, that you know they don't change in during a chemical reaction, right? So the addition of a catalyst to a reaction won't affect the products formed as well, right? So it has nothing to do with the products, and you can just separate it, right? Using different separation techniques. So this was topic 2, rather simple. Now we move on to subtopic 3. It says that describe practical methods for investigating the rate of a reaction, including a change in mass of a reactant or a product, and the formation of a gas. This is one of my favorite topics in the entire syllabus of IGCSE Cambridge Chemistry. Because this is something that you need, and when you will be a researcher in the future, and your mind should be trained on how to plan a research or how to plan an experiment, right? If you wish to identify something, or conduct a research, if you have a hypothesis, so you must understand that what will be the requirement of a certain experiment, right? So in order to explain this, right? So what you need to do is that you need to define a few things first, right? And what are those things? We These are variables. Like we have independent variable, independent variable. There's another variable that is called a dependent variable, and the third type that is called controlled variable. Okay, so what are these variables? Independent variable. Okay, so let me read this again. Describe practical methods for investigating the rate of a reaction, including change in mass of a reactant or a product and the formation of a gas. Okay, so how do you let's come back to these in a minute. I need to explain this, that what they are exactly asking us, right? So when a chemical reaction takes place, for example, A plus B, and this is producing C and D, or let's take an actual reaction, let's say nitrogen, it is reacting with hydrogen and it is producing ammonia, and 2 moles of ammonia are produced, and when 1 mole of nitrogen and 3 moles of hydrogen gas, they are reacting together. So as the reaction begins, we will just have reactants and we will not have any product, right? And when the reaction starts, and so even gradually over time, the concentration of the reactants will go down, and the concentration of the products, it will increase, right? So uh, here you can calculate the speed of a reaction by observing the products, I mean the reactants, because the more quickly, let's say the more quickly the reactants are disappearing, it means that the reaction is fast, right? And if the reactants are disappearing slowly, it means that the reaction is slow. Similarly, you can also measure the speed of a reaction, the rate of a reaction, by observing products, right? If the products are producing more quickly over time, let's say you are calculating the mass of the product produced after every 5 or 10 seconds, right? So you will see that how quickly the mass is producing. If the mass, and the products are being produced by looking at your graph. So let's say you can make a table like this, that mass of the of products, right? Mass of a product, and then time. So at when time is zero, when time is zero, the mass of the product is zero, right? So I should write this time on the other side. Let me just shift this. Oops. Let me just lock this. Okay. Yeah. I hope I'm able to copy this or move this. Yep. All right. Perfect. Okay. So when time is zero, the mass of the product is zero. When time is 5 seconds, the mass of the product is, let's say, 10 grams, right? And if, let's say, after 10 seconds, mass is 26 grams. And let's say you are observing a reaction where when you observe the mass of the product produced, when you measure it using a balance, of course. So it will be like in 0 seconds, the mass of the product is zero, and at 5 seconds, mass is, let's say, 6 grams, and after 10 seconds, mass is, let's say, 12 grams. So you can see that this reaction is slow because less mass is being produced over time, and this reaction is more fast because more mass is being produced, right, as compared to this one. So this is how, by observing reactants or products, we can figure out that by looking at this table, you can also make it change it into a graph, plot these values on a graph, and see that how the curve is changing and stuff, which we will see at the end of this lesson, because it is included in this syllabus. It is a bit lengthy topic, so let's continue. Yeah, so now you can imagine that if you have to measure time, so you need a stopwatch, right? So you need a stopwatch, the in as a practical method, right? And you need a measuring balance, because you have to weigh the mass of the product produced, or the mass of the reactant being consumed. So we need a measuring balance, right? And if a gas is if a product produced is a gas, right, so then you need a gas syringe. It is a special type of equipment. It is a, made of glass, or sometimes it might be made of a plastic. So where you can calculate the volume of a gas produced, right? So gas syringe, and a thermometer, because we might be looking at the temperature as well, and then a beaker, because sometimes in some reaction in a product, with the product produced, a precipitate is produced, right? So you will see that how quickly this precipitate is being produced. For example, you can draw a cross on a paper, and then you place that beaker on this paper, and the more quickly this you are unable to see this cross through the beaker, it means that the precipitate is being produced more quickly, right? And if this cross takes time to disappear, if you look through the speaker, so that would mean that the precipitate is being produced slowly, and and that is why the react it's the time is being taken to this cross to disappear when we look through the speaker. Anyways, so this is how you basically figure out that what will be the apparatus that will be required. So now I think I've explained the uh, you know uh, the rest of the topics, or the connected topics. So now let me come back to independent or variable and dependent variable. So independent variable is the factor being changed. So I'm going to write here factor being changed, right? So what is meant by factor being changed? Like for example, a temperature interval, like you are measuring temperature, that what will be the reaction. Let's say if you are studying the effect of increasing temperature on the rate of a reaction, so you will conduct the experiment first at 0 degrees Celsius, then you will repeat the same experiment at 10 degrees Celsius, and then you will repeat the same experiment at 20 degrees Celsius, and then you will start over again at 30, and then 40, and. So let's say you wish to observe the change of a temperature on the rate of a chemical reaction, and this is the range that you have selected, that you will see that what will be the rate of reaction in this range, starting from 0 all the way to 40 degrees Celsius, right? So that is why we need a thermometer. So this is why I included a thermometer is also necessary. Okay, so the factor being changed, so temperature here is our independent variable, right? We are changing the temperature to see that what will be the effect of that change on the reaction. So that is independent variable, right? And now what is a dependent variable? Dependent variable, the variable being measured. So variable being measured. And in this case, it's the mass of the product formed, right? Mass of the product formed, or the product may be a gas, so the volume of the gas produced, it depends that what the state of the product is, right? So now we are observing that by increasing temperature, what is happening to the mass of the product over time, right? So that is our that is our dependent variable. And then we have third type of variable that is called control variables. So if you are trying to understand the relationship of increasing temperature on the rate of a reaction, so all other aspects must be kept constant. For example, you know, uh, you know, every factor that could affect the rate of a reaction besides the independent variable, that must be kept constant. For example, concentration must be kept constant each time when you repeat this reaction, right? So concentration, otherwise you will not be able to correctly identify only the effect of the temperature, if you don't keep the other things constant, then if you are not keeping the concentration and other things constant, then you will not be able to correctly calculate that what was the effect of the temperature on the rate of reaction entirely, because now it may involve some, it may have some input from the concentration and surface area and stuff. So concentration must be constant, surface area must be constant, and catalyst, if you are adding a catalyst, using a catalyst, then use in all these reactions. If you're not using a catalyst, then don't use a catalyst at all, because if you're just uh, trying to understand the effect of temperature. Now let's say if you wish to see the effect of surface area on the rate of reaction, then temperature must be kept constant, concentration must be kept constant, and the use of catalyst must be the same. And only then you can use the surface area. For example, you are but the mass must also be the same. Let's say you have a mass of 2 grams of charcoal, but it's a lump, and then you burn it, and you see that how much time it takes to burn, and then you repeat this experiment by using the same 2 grams of charcoal, but this time you crush it, you increased the surface area, right? You changed it into a powdered form, and now you see that how quickly it burns, right? So the mass of the charcoal used must be the same, only the surface area can be changed, right? And then yeah, and all the other things must also be kept constant, right? So this is why these are very, very important, for research, planning, and conducting experiments, because this can ruin your entire experiment, because like if you don't take care of these things, independent, if you don't define them at the beginning of the reaction. So yeah, so I hope I talked enough about this. Now, uh, you know, yeah, I think we have talked enough that that how will you study the effect of the temperature change on the rate of a reaction, right? So you compare the temperatures with the mass of the products being produced, right? And then you can draw a table like this, that at when the reaction was at 0 degrees Celsius, so uh, you know uh, the products produced in 5 minutes, and in 5 minutes, um, you know uh, 2 grams of a product was produced, and then at 10 seconds, in 5 minutes, there was 9 grams of product got produced, and then at 20 seconds, after 5 minutes, the product produced was 20 grams, right? So you can see that as you are increasing temperature, the product is increasing as well, right? Or the same amount of a product might be produced, but it will take less and less time. Okay, no, let me just make this correction. So the mass of the product produced will remain constant, only the time taken will decrease, right? So this is two grams for all of them, 2 grams and 2 grams, yeah. At 0 degrees centigrade, in order to produce 2 grams, the total time that the reaction is taking is, let's say, yeah, 5 minutes, right? And when you increase temperature, from 0 to 10, now it will be, 3 minutes, right? And this is 3 minutes. And at 20 degrees Celsius, now let's say the same amount, 2 grams, is now being produced in just 1.5 minutes, right? So now you can see that the reaction is increasing. The rate of the reaction is increasing with increasing temperature, because less time is being used in order to produce the same amount of a substance, right? So I hope this is clear. Now, interpret data, including graphs from the rate of reaction experiments. Okay, so usually the rate time graph, it looks something like this. Let me just draw it here. On this axis, we plot time, and we use seconds as a unit, right? And uh, and on this axis, we use mass of the product formed. So mass of the product formed, right? So now the graphs showing the rate of reaction will have the mass volume of product formed on the y-axis. Let's call this one y, and time on the x-axis. So this is x, and that's y. So now, if you need to learn, to read the curves. So if the curve is like this, and if another curve is like this, so the red one, it will have. Let me just draw it more steeper. Yeah. Okay, so now you can see that the red curve is more steeper than the black one. So this one is more steep, right? So the red one, uh, it is steeper, right, as compared to the black one. So here and here, yeah. So the more steeper the curve, the faster will be the rate of reaction, right? And this one will finish sooner, and because you can see the straight line, and the black one, it's going to take time, so this will finish later, right? So this is how you interpret data, including graphs from the rate of reaction experiments. And yeah, so you remember that once the line becomes horizontal, this indicates that all the products have been formed, so the reaction is complete, right? And now yeah, now in order to calculate the rate of a reaction at the start of a reaction, or at a specific time, a tangent is drawn, right? So I hope you understand how to draw a tangent. So tangent is a straight line that touches the curved line at a specific point. So let me just paste this image for you guys, and explain how do you draw a tangent, right? So tangent is, let's say this is the graph, after plotting our values on the graph. So on this axis, y-axis, we have volume of gas produced in centimeters cubed, and this is on the x-axis, we have time. So let's say I wish to calculate the time, or the rate of this reaction at 5 seconds, right? So this is 5 seconds, and you see, this is where I mark, right, on the curve. So I mark this location because it is right above 5 seconds, right? So once you do that, now you draw a tangent, right? So let me explain what a tangent is. So tangent is a line that's gonna touch this point, only one point on this curve, right? So you take a ruler and you place it here, and when you place a ruler on the curve, so remember that there should be equal distance on both sides, right? And that is when and you place it outside the curve, right? Don't place a ruler here on the inner side of the curve, because if you place your ruler on the right side of the curve, below the curve. So what will happen? So the tangent that you, the line that you will draw, it may touch 2 points, on this curve, right? So it should be on the outer side of the curve. And yeah, again, tangent is a line that must, touch only one point of this curve. So once you do that, then you draw a triangle, right? So and you can draw it, anywhere you like, so we draw it like this, the way you, like, you are looking at on the diagram. So yeah, and then you use this formula, like change in, the concentration versus change in time, right? So change in concentration divided by the change in time, and that's going to give you the, instantaneous rate, or the rate of this reaction at 5 seconds, right? So you can see here that this line of the triangle, it is touching this value of 25 centimeters cubed. And uh, on this axis, yeah, here this line is touching at 5, right? So it's 25 minus 5, final minus initial, you get 20, right? That's the change in concentration. And now calculate the time. So time here, it is 0 seconds, and here it is 10 seconds, right? So final minus initial, so this is 10 minus 0, we get 10 seconds, right? So then you calculate the gradient by putting the values. So 20 divided by 10, so the rate at 5 seconds is 2 centimeters cubed per second, right? So this is how you calculate an instantaneous rate at any given point on this curve, right? So how about now you try to calculate the rate from this graph at 20 seconds, right? So give me the answers in the comments below. And yeah, I think this will be all for today. And our next part of the same lesson will be the supplement topics. So don't forget to watch that if you are registered for the extended version of this course. So this will be all for today. I'll see you in the next one. Take care. Goodbye.